Hi everyone. In the part 2 of the lecture 6, we will study an efficient way to analyze a circuit with a diode. In this method, we cannot expect an exact solution. However, intuition from this method is much more valuable to us than an exact solution without understanding the operation of a circuit. We have 6 different IV curves of a single diode with I sub s equal to 5 times 10 to the minus 16 ampere. 6 different curves are drawn with different maximum values of the diode current. All of them look quite similar. In other words, in any linear scale, the diode IV curve always shows sudden increase from almost negligible current to a large enough value. The slope is quite steep. The exponential dependence of the diode current on the diode voltage is the previous graphs. In this figure, the IV curve is drawn in a semi-logarithmic scale. A difference by a large tick in the y-axis represents a 10 times difference. As shown in the figure, in order to obtain 10 times larger current, we must apply only 60 millivolt 0.06 volt additionally. Within such a small voltage difference, the diode current can easily hit the maximum Y value. Inspired by the previous observation, we can introduce a constant voltage model for the diode. In this model, we have two phases. These two phases are separated by a constant voltage. In Rajavi's textbook, it is denoted VD on. Its value depends on the diode and the current level. Anyway, it is usually in a range from 0.7 volt to 0.8 volt. When the applied voltage is lower than this voltage, the diode does not conduct a current. Also, an abrupt increase of the diode current is assumed at VD on. At first glance, the abrupt increase introduces some confusion to students. How can we have a vertical line? It is not possible. A vertical line does not have a unique value. That is a natural question. The vertical line in the constant voltage model should be interpreted as a limiting case of a very steep slope. In order to have a larger current, even in this case, we must apply a larger voltage. But the additional voltage is extremely small in this model. Such a small voltage is neglected in an approximate estimation. Let's solve our previous problem introduced in the part 1. In this time, use the constant voltage model. In this model, first, we must determine whether the diode is turned on or turned off. Assume that the diode is turned off. Then, the diode does not conduct a current. The circuit schematic actually becomes like this. Obviously, V out must be 0 volt. However, it means that 1 volt is applied to the diode. Since 1 volt is certainly larger than VD on, our assumption does not hold. Instead, we assume that the diode is turned on. Then, the diode can conduct a large current. But the voltage across the diode cannot exceed VD on. Therefore, V out must be 1 volt minus VD on. Then, is it 0.3 volt or 0.2 volt? It depends on VD on, and usually the problem specifies its value. Anyway, for VD on from 0.7 volt to 0.8 volt, the current would be around 0.2 milliampere or 0.3 milliampere. We don't solve the nonlinear equation. By using a simplified model for a diode, we can get a good approximate solution. Well, some students would not be happy with such an approximate solution, but an approximate solution obtained from the constant voltage model can be used as a good starting point for the exact solution. The figure shows R over V out again. Previously, we had no idea about the solution, but now we know that the diode must be turned on and V out is about 0.2 volt or 0.3 volt. The exact solution can be much easily found as soon as an approximate solution is available. In the next video, some applications will be presented. Thank you.